class, welcome back for today's another lesson of circular motion. This is class by Raj, teaching for physics from 6 semester 1. Today we are going to continue back our lesson on circular motion, where we are going to look on the centripetal force. Now the learning outcome for today's lesson is we need to explain that a uniform circular motion is due to the action of a resultant force. You see class, when an object performs a circular motion, there must be a force that is making it to perform that motion. And that force must be directed towards the center. That force that is directed towards the center is called as a centripetal force. And centripetal force is not a special force class, but it's just actually a resultant force based on Newton's second law.
I want to add up a bit here. Okay, now when we know the acceleration is centripetal acceleration is v omega, and then we know a equals to r omega square, and then we know a equals to v square over r, and then we know that the delta v here, okay, the delta v here over the delta t, a equals to delta v over delta t, okay, gives you the acceleration. Okay, delta t is time taken from here to here. So the direction of the delta v, if theta is small, is towards the center. If theta is getting smaller and smaller, the direction will be towards the center. Okay, now as we know, our next lesson is whenever there is a centripetal acceleration, whenever there's an acceleration okay, there must be a force. There must be what? There must be a force. We know that whenever there is an acceleration, there must be a force. Okay, there must be a force. When particle is in the circular motion, it has an acceleration of v square over r towards the center of the circle. Okay, now according to Newton's second law, based on what he says, the resultant force F is equals to ma, correct? Now what is F? F is called as centripetal force. Centripetal force is a force towards the center. Okay, it's a force where towards the center. So when object is performing a circular motion, an object can only perform a circular motion when it has a centripetal force. A centripetal force is not a special force, not like as if like if you have tension, you have friction. No. Centripetal force is actually just an resultant force. It can be any force, but it's just an resultant force. So that means if there is a centripetal force, an object can perform a circular motion. Okay, an object can perform a circular motion. That means there must be a force towards the center, which is A, which also the acceleration is towards the center. Okay, if there is no force towards the center, the object which is here cannot perform a circular motion, but the object will move in the direction of v, which is a linear motion. Okay, again I repeat that when an object is actually performing a circular motion, there must be a force that's making it to form a circular motion. That force is called as centripetal force. Centripetal force is a resultant force. It's not a special force. It can be any force that is towards the center. As long as there is any force towards the center, then that object will perform a circular motion. If just say there is no centripetal force, then this object cannot move in a circular motion, but it will move in a linear motion. It will be directed away and perform a linear motion. Okay, now just because centripetal force A, we have three formulas. Okay, one is, I'm going to write down with a different color pen. One is we have A equals to V omega, R omega square, V square over R. So when we substitute these three formulas, so centripetal force also got 3. which is F equals to mv omega, F equals to mr omega square, F equals to mv square over r. So these are the three formulas of centripetal force. So what we are going to do now is we are going to use the concept. Okay, so now class, we already understand all those quantities. Okay, we know that in circular motion we have all these quantities. We have to talk about angular displacement, we have to talk about velocity, linear velocity, angular velocity omega. Angular velocity omega, if I want to draw, I can draw it in this way. Since the object is moving in this direction, I can draw it in this way. This is omega if I want to know the direction lah of omega. Okay, then we have what? We have period, we have frequency. Okay, then we have another quantity which is the acceleration. This is called as centripetal acceleration. Why? Because the acceleration is towards the center. And then we have also centripetal force, which is because of the acceleration there is a force also towards the center, and the force is called as centripetal force, and we have three formulas. So now, knowing all this concept, we need to apply this concept. Now what is important here in the exam is, every time in the exam what they like to emphasize is, they love to emphasize the concept of the speed and velocity. Okay, they like to ask, they want to know whether you understand the speed and the velocity. Why the speed and the velocity are two different things in the circular motion? It is because of its direction. And then another one they love to ask is how to derive the acceleration. Okay, how to understand this concept through this graph. So these are quite famous in the past years. So you have to know about this. You have to know about this. Okay, so these are famous, and we will do past years and you will see that. Alright, so that is for centripetal force.
Now, after knowing all the concepts and all the quantities that is involved in a circular motion, like the angular displacement, angular velocity, linear velocity, period, frequency, centripetal acceleration, and centripetal force, now it's time to do the application of all these concepts and quantities in an examples. So let's solve problem involving a uniform horizontal circular motion for a point mass and a solve problem involving uniform vertical circular motion for a point mass.
The concept on the motion on a horizontal circle, and we're going to apply the concept in this example. Now what we have here is, we shows a stone of mass m at the end of a string being whirled around in a horizontal circle, okay, of radius r on a smooth surface. Okay, so the person is whirling around like this. Alright, okay, now what shall we do in this kind of question? If the stone can perform the circular motion, definitely there is a centripetal force. There is a centripetal force. Okay, so what we do is, we want to find out what is the centripetal force. What we do now is we draw first the forces. Every time I've been telling you, draw first the force, draw first the force. Okay, let's look at what is the first force that is being in this diagram. We can draw. First is mg. Okay, here is mg. Alright, and then because this is a string, then we have here is tension. Okay, so that is the only force. Alright, so there is a centripetal force here that's making the stone to go around, perform a circular motion. So the centripetal force that is making the object, the stone, to perform a circular motion will be the tension. Because why? Tension is towards the center, is the force that is towards the center. So tension becomes the centripetal force in this example. Okay, tension is the centripetal force. Okay, alright, because it's towards the center, it's towards the center of the circular motion. So therefore, there's a centripetal force, right? And then we know that the resultant force, centripetal force, F is equals to ma. Now we can substitute a as whatever we want. You can also put a, you can use three formulas, whichever you want according to your choice of questions. A is r omega square, F equals to mv square over r. We can also put F equals to mv omega. Okay, we can use whichever we want. So in this example, what I'm going to do, I'm going to just follow whatever the book has done. So I'm going to use this formula. Okay, you can use either three, yeah, but I'm going to use this formula. Okay, so here the centripetal force is mv square over r, and in this diagram the centripetal force is the tension. So I can say T is equals to mv square over r. Okay, alright, what is V? V is the speed of the stone, which I'm going to draw here. Now the V is the speed of the stone, which is in this direction. Okay, which is tangent. So the speed of the stone is V. Just say in case if the string snap, okay, snap, that means what? There is no resultant force on the stone. Okay, so there is no tension that is exerted on the stone. So according to Newton's first law, the stone will move along a straight line. So it will move and follow the direction of the V. Okay, so it will move and follow the direction of the V. Okay, alright, which is tangent to the circle. So the stone will move in this direction. Alright, okay, that's all. Let's look at conical pendulum. Now we know the concepts of these quantities in the circular motion. We are just now learning how to apply the concept in some examples, and for now it is about conical pendulum. Okay, we have a string which is length L, okay, fixed to a bob of mass M. Okay, alright, so what happens is at the end of the string, okay, this is like this, right? At the end of the string, with an angle of theta, we make the bob to make a circular motion. Okay, so a conical pendulum is formed when a bob of mass M at the end of a string is whirled in a horizontal circle of radius r. So from here we have the string and then it is whirled around. Okay, alright, with an angle of theta from the vertical. So we have here is the length L, okay, and then we have a mass M, and then we have a force here. Okay, so this one is actually tension. Okay, then this string with an angle of theta to the vertical. Okay, so this was the center, so it is whirled around horizontal with an angle of theta. Okay, so a conical pendulum is formed. Okay, so then what happened is we resolve the force. Okay, we resolve the force. So here, if I resolve here, the theta here is this is theta, and then here becomes what? Okay, here becomes F in this direction. Okay, because it is in that direction, here become this direction, here become F cos theta, and then here becomes F sin theta. Okay, alright, so now what we do is that, okay, we find the resultant force to the center. So if you see the resultant force to the center, there is only one resultant force to the center, which is F sin theta. Okay, so the resultant force to the center is the centripetal force. So F sin theta, which I'm going to write down here, F sin theta is the centripetal force, which I can put whatever I want to put, class. I can put mr omega square, I can put mv square over r, I can put mv omega, but I'm going to follow the book, so I'm going to put mr omega square. Okay, number 1. Okay, I got the concept. And then this one is equals to this one. Okay, so I'm going to write down here f cos theta is equals to what? Is equals to mg, number 2. Then we already know the concept of force. What we can do is we want to do whatever we want to do, we can go ahead. Okay, if I want to find anything I want to find, I can go ahead. But the book wants to find period, so I can go ahead and do whatever I want to do. Okay, so here I have here f sine theta is mr omega square. If I want to replace this is extra additional. Yeah, the concept is to understand this and get this. Okay, so here if I draw this triangle, this will be theta, this will be L, this will be R. Correct? So here sine theta is R over L. So R is L sine theta. Correct? This is all additional. So I can substitute in number 1. F sine theta is equals to M L. R is what? ML sine theta omega square. I can substitute the R here. So what do I get? I get F equals to ML omega square. Okay, these are just additional. Okay, and then if I want to substitute this F inside here also, I can substitute. So F is ML omega square. So I put ML omega square cos theta is equals to mg. Okay, is equals to mg. So therefore I cancel and cancel m. So what do I get? I get omega is equals to g over L cos theta and then square root. Okay, I can also do that. I can find my omega. I can find my omega. Okay, then I can do what? I can find my period. Okay, the period of the oscillation. So what do? You can find, you know, T is equals to 2 pi over omega. So then you can find T equals to, you substitute this, 2 pi over G over L cos theta. So what do you get? You get 2 pi L cos theta over G. Okay, you can also go ahead and find frequency also can. If I want to go more than that, I also can find. So what is frequency? Frequency is 1 over T. So I get 1 over 2 pi L cos theta over G. So what do I get? I get 1 over 2 pi L cos theta over G. I get 1 over 2 to find frequency also can. So you realize how I find frequency is 1 over T, this 1 over T, so I can just find my frequency. So there are many things to find, class, but the concept is, I apply the concept in the beginning. The concept is to find the resultant force to the center. That resultant force will be the centripetal force. So this is we applying for the example of conical pendulum. Okay, all right. Now let's look on the motion of a cyclist going around a curved track. Now this motion of a cyclist going around a curved track can be found in your Oxford Fajar book, page 117. Okay, we have a cyclist here. Okay, is going around a curved track. So this is the curved track, so it's going around like this. Okay, it's going around like this. And as he goes, you realize that he has bent his body. Okay, his body, his position of his body is like this, but he has bent as he goes around the curved. So you realize that he has bent his body. So this kind of questions, what is the first thing to do, which I've always told you all. The first thing is to do is to draw the forces. Okay, so the first one, what we should do, we should draw the forces. Okay, so now here we have the center of gravity, which is G. G is called as what? Is the center of gravity. Okay, so from the center of gravity we have the weight. The first force is the weight, okay, W. Alright, then we also have another force which we know this is the surface. Alright, so this will be the frictional force. F will be the frictional force, which is towards the center. So this is the center of the circle. So F will be the frictional force. And then after that, from here, from the surface, we have this normal force. Okay, we have this normal force, which is R. Okay, where R is called as normal force. So that's it. There's three forces that acts on the cyclist. Alright. So now what we are going to do is that the first concept, we are going to apply the first concept. Now the first concept is, okay, now as the cyclist is making a turn in the roundabout or going around a curved track, okay, so what happens is we look at the frictional force, because frictional force is towards the center, so frictional force will be the centripetal force. Centripetal force will be who? Will be the frictional force. Because why? Because there's only one force that is towards the center, so it's the frictional force. So the frictional force is the resultant force, and the resultant force is the centripetal force. Okay, so centripetal force is equals to MA. So centripetal force is the frictional force, okay, which is equals to MA. So A I can substitute with whichever I want, but I choose to follow what is in the book. So I put MV square over R. Okay, V will be the velocity, okay, the linear velocity, and then R will be the radius of the curved track. Okay, R will be the radius of the curved track. Okay, so we haven't finished yet, yeah, because this is the first concept. So if you look at the first concept, which is this concept comes from the concept of circular motion concept. Okay, there is also another concept which we have to apply in this in order to study a little bit more about the motion of the cyclist, which I'm going to write down here. The concept can be found in under the chapter of static, okay, which is the concept of moment of forces. Yeah, you haven't studied this yet, but you just understand. So when I teach this chapter in static, which I'm going to do it after this lesson, then you will understand more better. We will try to learn how to apply this concept in many other questions. So moment of force is also called as torque. Moment of force is also called as torque. Now what is torque? Torque is also like a turning effect. It's a turning effect. It's a turning effect. You need torque in order for an object to rotate. So torque is actually a measure how much a force acting on an object causes that object to rotate. Again, torque is actually a measure of how much a force acting on an object causes that object to rotate. So torque is actually by formula is F times with R. F is the force, R is the distance. Okay, the distance. All right. So the condition is the F and the R must be perpendicular. Must be what? Must be perpendicular. So in order to apply this concept inside here, one more thing I forgot, the symbol of torque will be like a tau. Okay, alright. So in order to apply inside this example, we know that the concept says the clockwise moment about G. The clockwise moment about G is equals to the anti-clockwise moment about G. Okay, clockwise moment about G is equals to anti-clockwise moment about G. So who is moment referred to? Moment is referred to torque, moment of forces, which is referring to torque, which you have to take F times with R, where you must find the R which is perpendicular to the force. Okay, so here if I want to apply in this concept, okay, let's look at this diagram. Okay, so it says the word about G. Now what is it meaning about G? So we're going to choose one um, force. Okay, whichever we want to choose, we choose, but we choose to follow the book. Okay, so we're going to choose this one. Okay, about G. That means about G means we take the moment about G. Okay, so we take the moment about G. So whatever forces that is in this line, okay, we don't include in the formula. Actually, if you include also, it will become 0. Okay, because of the R. Alright, so we just take this line here, we just put this about G. Okay, so moment about G. Okay, alright, so what do? Then we have two forces here. One is R and one is F. Okay, so I'm going to take a green color. I'm going to look at R. R is this one. This is R, correct? This is R. So how I want to know whether R is clockwise or anti-clockwise? Okay, so this is the moment I take about G. So towards the moment I take, so it will be in this direction. Okay, in this direction. So it's in the direction of anti-clockwise. Okay, alright, then it's a direction of anti-clockwise. So F times R, R is the force, times with the distance. So the distance must be perpendicular. So if I look at that, the distance must be from the force to the moment about G, which is the A. Okay, so it must be from the force R to the moment about G, which is A. So R times A. Okay, if you don't understand, if you feel like you don't quite understand it, it's okay, because I'm going to teach more about it in the next chapter, but it will be the similar way of teaching class. Okay, so I'm actually teaching very detailed here. All right, so here I take again moment about G. Okay, moment about G, and then I take the next force, which is the F. Okay, so F. So if I towards the moment about G, you will notice that it's in this direction. Okay, I'm going towards my this, so it will be in that direction. So it is clockwise. Okay, it's clockwise. So it is F times with the distance which is perpendicular. So if you realize here, the distance that is perpendicular, okay, this is the force, so the distance that is perpendicular, which will be this, correct, which is H, okay, it will be this, which is H. Alright, okay, so what do? We times F times H. Okay, F times H is equals to RA. So F is what? F is mv square over R from the first concept. Okay, from the first concept, mv square over R, H equals to R times A. And we know R is equals to mg. Okay, upward force is equals to below force. So R is equals to mg. So mv square over R, H equals to mga. Okay, alright, we can cancel this. V square over R, H is equals to A. But we don't stop there. So let's look at this now. Again, another one more, which I'm going to take this color of pen. Okay, so we look at this triangle here. Okay, this triangle here, 1, 2, 3. Okay, so if I draw it like this will be theta, this will be H, this will be A, correct? So that means tangent theta equals to A over H. So here, wait, I missed out V square R H A. Okay, so wait, I missed out my G, mg. Okay, sorry, I missed out my G here. A, so here will be a G, correct or not? So V square over RG is equals to A over H. Correct? G, I missed out my G. Okay, so here tangent theta, A over H is tangent theta. Tangent theta is equals to V square over RG. Okay, so tangent theta. So this tangent theta is also same as this tangent theta. Okay, now what does it mean? Why is that tangent theta is so important? Why is the theta actually so important? Okay, if theta is big or large, it's a large angle. That means if the theta is large, that means this angle, okay, this angle, okay, sorry for that, this angle, that means this angle, okay, this is theta, correct? This theta is big, the angle from this is big. Okay, what happens? That means the speed v increases. Tangent theta is big, v increases, correct? Okay, and the radius of the curved track is small. So if tangent theta is big, curved track is small, so r decreases. Okay, so what does it mean? That means if a cyclist is going through a curved track, if the cyclist is going through with a very if you take a roundabout, and the cyclist, you're speeding in the roundabout, instead of braking, instead of like you brake, okay, and then you speed across the roundabout, what will happen is that you must make sure you lean your body, you increase your angle theta, therefore you can make a complete circle. Okay, again I say, yeah, all right, if you're going in the roundabout with a very large velocity, okay, you're going very fast in the roundabout, so what you must do is that when you want to make sure you take a proper curve, what you must do is you must make sure you lean your body, okay, so that you will take the curve, you must take the complete circle here. Okay, all right, or if you don't do that, what you can do is that if you're going near to the roundabout, okay, you must make sure you lean your, you decrease your radius of your curved track, and then you increase your theta. Okay, so that's what it's trying to say here. Okay, so if you look at your textbook here, it says the cyclist has to lean through a larger angle, when his speed v increases if the radius of the curved track is smaller. Okay, speed v increases and track is smaller. So if you see in this page, class, if you see in this page, there are two concepts here. This is the first concept, which is from the circular motion. This is another concept, is actually from the equilibrium of rigid body. Okay, is the concept of equilibrium of rigid body, which is from the concept of moment. It's under the chapter of equilibrium of rigid body. So it's the concept of moment. Okay, now the cyclist has to lean inward in order to produce an anti-clockwise moment to counter the clockwise moment. Okay, so that he will not have a fall. Okay, all right, so that is it for this. Okay, now let's look at motion in a vertical circle, which is page 119. Okay, now we have a stone of mass m. Okay, we have a stone of mass m, okay, being whirled in a vertical circle. Okay, remember this is a vertical circle. Okay, this is the center. Okay, with constant angular velocity omega. So constant angular velocity omega. So omega is constant. Okay, so now what we want to know is that we want to solve this by stages, because why? In a vertical circle, the stone will have a different kind of resultant force due to the gravity, because vertical circle means, that means it's affected by gravity, correct? All right, so let's solve first in this first position, which I'm going to take this color pen. This is point A. Okay, now the stone is here in point A. So what is the first thing we do? We draw the forces. Okay, we draw the forces. So this will be the tension. This will be the mg. Okay, so what is the force to the center? Mg. Okay, what will be the force that is involved in the center? It will be T and also mg. So the resultant force will be T minus mg. T minus mg is equals to what? Is equals to m. You can put whatever a you want to put. I'm going to go on with mr omega square. So you got T minus mg equals to mr omega square. Then you get T equals to mg plus mr omega square. Okay. Now the stone in position B. Position B. Okay, so we have the stone here now in position B. This is the string. Okay, so now we draw the forces. First we draw the forces. Okay, I'm going to get red pen. Okay, so this will be the tension in the string. The mass will be like this. Okay, and then here will be theta from this vertical here, theta. So if I draw this, okay, this will be theta. Okay, so here I have to resolve this mg. I have to resolve. Resolve means you resolve to vertical and horizontal. So this one will be mg cos theta. This one will be mg sin theta. Okay, now we look the forces that is involved to the center, which is T and mg cos theta. Because mg cos theta is opposite direction to T, so the resultant force will be T minus mg cos theta equals to mr omega square. So T is equals to mg cos theta plus mr omega square. Okay, now the stone is here. Okay, this is a string. Okay, what's the first thing I do? I draw the forces. This is the force mg. This is the tension T. Okay, so the forces here is T, tension. Okay, to the center is only what? Is only tension. Okay, so the formula will be the resultant force T is equals to mr omega square. This one I just put like this. Okay, next position I'm going to take is, I'm going to use this color. What if it's in the next position, which is the position is this position, which is C. Here, C. Okay, whether I draw with black pen, showing that it's a string. Okay, the stone is there. So the first thing what we do is that we draw the forces. The tension is in this direction. The mg is in this direction. So how we can solve this? Both are in the same direction towards the center. Okay, so T plus mg is equals to what? Mr omega square. T is equals to mr omega square minus mg. So you see, when it's in the vertical circle, we have 4 different tension. Okay, that is experienced by the stone. Here it experiences mg plus mr omega square, where here will be the maximum tension at the position A. Agree? Okay, and then after that at point B, when theta is 90 degrees, you will realize T equals to mr omega square. Here is mg cos theta plus mr omega square. And then here is mr omega square minus mg. So this will be the least tension. That means minimum tension. Okay. Alright. Now, for the stone to be able to make a complete circle. So now the stone is going around here, is whirled around, it's going around here. In order it to come down, to make it a complete circle. So the tension at C, the tension here, this T, I'm going to flow up here. The tension here, mr omega square minus mg must be greater or equals to 0. That means the tension must be greater or equals to 0. Okay, for the stone to make, now the stone can go up, right? The stone has to come down to make a complete circle. So in order for the stone to do that, the condition is the tension must be bigger or equals to 0. That means what is the tension? mr omega square minus mg must be bigger or equals to 0. Okay, so let's take the minimum. Let's take the minimum value, which is mr omega square minus mg equals to 0. So mr omega square equals to mg. Therefore, we get omega is equals to g over r. Okay, square root g over r. Okay, m cancel, so omega is equals to square root g over r. So this is the minimum omega that you have to have, this thing has to have, in order for the stone to make a complete circle. Okay, so even if I don't want to put mr omega square class, I want to put other formulas also can, no problem. Okay, I can put T plus, okay, I'm going to just direct it here, yeah. Okay, T plus mg equals to mv square over r. Okay, so T is equals to mv square over r minus mg. So for the stone to make a complete circle, what has to happen? Mv square, T has to be greater or equals to 0. So the minimum will be mv square over r minus mg is equals to 0. So we get mv square over r equals to mg. So v square over r is equals to g. So v equals to square root gr. Okay, v equals to square root of gr. So this also we can say this is the minimum velocity the stone has to have in order for it to make a complete circle. Okay, alright, at the highest point, so the v has to be minimum value, so this will be the v. Okay, alright.